Hi guys, welcome back to In Case of Econ Struggles. Today I'm going to keep talking about the overlapping generations model. I'm going to provide just an alternative model to the one we saw in part 1, where basically in this model I'm going to use investment and savings, and instead of endowments we're going to have production with firms and labor. The reason I'm doing this video is some of you may have seen a slightly different version of the OLG model that I presented in part 1, so I just want to present this version as well in case it's helpful. And as usual, timestamps are below if you'd like to jump around, but let's get right into it. So the outline for how this video is going to go is first I'm just going to talk about how the updated setup works with savings and firms. I'm going to talk about willingness to save and optimal savings in this OLG model. And that means I'm going to talk about steady state capital per person, where again we're going to use K for capital. And then at the end of the video, I'm going to do a numerical example. I'm going to show that the savings rate is too high in this world just as it is. And then in the next part, I'm going to discuss how we can improve upon what happens in this version and how we can get to a more optimal allocation between the younger and the older generations. Okay, so the way this works, I'm once again going to talk about coconuts, is that we've got two generations, they overlap in one period. I'm going to have Bill when he's young and Bill when he's old, and both people are going to eat coconuts. The number of coconuts that Bill eats when he's young is going to be CTY. The number of coconuts Bill eats when he's old is going to be CTO, or CT old. We're going to have some coconut trees. That's going to be our capital in this economy. What's going to happen is that when Bill is young, what he can do is he can save some coconuts for tomorrow. The way he's going to save is he's going to plant those coconuts so that in the next period when he's old, and again, we're bringing in firms. So when we bring in firms, we're also going to have firms. What we're going to do is Bill when he's young, he's going to supply the labor to the firms. The firms are going to pay Bill when he's young a wage WT. Now when he's old, Bill's going to have the coconut trees that firms are going to rent. They're going to rent that for a rental rate RT. The number of trees that Bill rents to firms is going to be capital or KT. And again, we're going to have some consumption when Bill is young. The consumption that Bill eats when he's young is just the wage that he gets minus whatever he chooses to save. Because again, when he's young, Bill can choose to save some coconuts or plant some coconuts to become coconut trees in the next period when he's old. So now let's start thinking about the objective function for Bill. So Bill's objective function for both periods of his life, he's going to have a utility function over the coconuts he eats when he's young and the coconuts he eats when he's old. When he's young, maybe that's just some function u of CT and some u of CT old. And then we have this beta or this time discounting, which is pretty standard. So I'm just going to throw that back in. For his budget constraints, when he's young, we know that the number of coconuts that Bill eats is just his wage minus his savings. That's going to be in terms of today. If I think about when he's old, right, Bill is trying to think about how much to eat and save and all these things when he's young. So the number of coconuts that he eats when he's old is just the interest rate times his savings. But that's going to be in the future, right, because that's not today when Bill's thinking about how much to eat when he's young and old. This old consumption is one period in the future, so we're going to need to use present value in order to discount this back. We're going to discount this back by the real interest rate, so we're going to divide that by 1 plus RT plus 1. And so we get 2A, which is really the present value of that second budget constraint. And if I put these two budget constraints together, both number 1 and number 2A, I'm just going to solve and I'm going to get this equation right here. So now that we know what's happening for Bill, let's think about what's happening for firms. So we have a profit function for firms, which is just their output minus their cost, where here's their labor cost and here's their capital cost. It's going to be just some function of capital and labor for Y minus depreciation, because we're going to say that trees die from one period to the next period. We're going to assume for this production function, we're going to assume that we have constant returns to scale, which means that in our profit maximization problem, our profit is going to be 0. Now, of course, if we remember from profit maximization, the wage and the rental rate are going to be based on the marginal product of labor. So whatever this marginal product is, whatever this marginal profit is minus depreciation, that's what we're going to pay in terms of the wage and the rental rate in this economy. So now that we know sort of optimal consumption, we know what the wage and what the rental rate is, the last piece we need to figure out is how much Bill wants to save when he's young for when he's old. And that's going to come out of this utility maximization problem. So all I've done is I've rewritten the utility maximization problem. I've put in the budget constraint, the combined budget constraint equation 3 in here, and I'm just going to take some first order conditions and use that to get what the optimal savings should be. So I'm just going to take a first order condition for consumption when young, consumption when old. That's going to look something like this. And all I'm going to do is I'm going to solve this to get some sort of Euler equation, which we know from previous models which looks something like this, where basically the marginal ratio of substitution between consumption when young and old has to be some discount rate times 1 plus the real interest rate. So now I've got this Euler equation, and I got to think about how this is going to relate to savings. Well, what this is going to mean is if I take this individual discount rate beta and I compare it to the economy discount rate, which is 1 over 1 plus RT plus 1, if they're equal to each other, then Bill's going to perfectly consumption smooth, because the rate in which he's willing to trade off between today and tomorrow is exactly equal to the rate at which coconuts do trade off between today and tomorrow. If Bill has a higher discount rate than the economy discount rate, what that's going to mean is that Bill is almost too patient. He's too patient relative to the economy, and so he's going to save too much for tomorrow today. Now, if he's not as patient as the economy discount rate, then he's going to save too little. He's going to consume too much today. If we can relate beta to the real interest rate, that'll sort of tell us whether we're saving too much, too little, or right about right in this model. So just as an example, let's take a utility function, and I'll just take a basic one with natural logs. And so I can say for this example that the amount that Bill eats when he's old is just going to be how much he eats when he's young times this sort of discount factor right here from the Euler equation. And I can use that to figure out CT old, CT young, and therefore savings. So that's exactly what I'm going to do. And so I'm just going to combine that with this equation right here from the budget constraint. I'm going to plug in, and because I'm going to get that CTY is 1 over 1 plus beta times WT, I know that savings is just equal to the wage minus consumption. So I'm just going to plug that in and get that this is the optimal savings right here. Again, I'm being kind of ambivalent about what marginal product of labor is, because I don't know the actual functional form of the production function yet in this example. Okay, so with that in mind, I know that the amount of coconut trees tomorrow is just the coconut trees that I plant today per person times the number of people, plus the amount of coconut trees that survive. So that's 1 minus the depreciation rate. And so I've just sort of written that out right here just to show you what that is, because now I want to think about number of coconut trees per person. And the reason why I want to think about coconut trees per person is I want to talk about a steady state, or a K star. When we talk about a steady state and we have population growth, we're thinking about number of coconut trees per person, not just number of coconut trees, period. So here's this equation right here, where I've got the number of coconut trees tomorrow, which is what I just did. I know that the number of people who exist tomorrow is just 1 plus population growth times the number of people today. And I want some KT plus 1 over LT plus 1. So I'm just going to do some math. I'm going to make some substitutions, and I'm going to get to this point right here. Now, once I'm to this point right here, I know what ST is because I just solved for that in the last slide. And so here's what ST is, and I'm just going to keep going with the math. Again, if any of the math is unclear, feel free to put a comment in the comment section below. But I'm just going through the algebra right now, and I'm trying to solve for K star, or the number of trees per person in the steady state. And I'm going to get K star is this guy right here, where it's going to be related to the population growth, the depreciation rate, and to beta, and to whatever the marginal product of labor is. So up to this point, it's been kind of vague. So what I want to do is I want to go through those exact same steps, but with a numerical example. So what I'm going to say is, here's a utility function, 1/3 natural log of CTY, 2/3 natural log of CT old. So our beta is 2. Let's say that we don't have population growth. Let's just make it easy. And for our production function, again, just to make it easy, let's say that we have full depreciation so that all the coconut trees die from one period to the next, and our number of coconut trees in the next period is just exactly equal to our savings from yesterday. So now I'm just going to plug in the math. So I know that W star is the marginal product of labor. So here's the marginal product of labor here. And so this is what we get. Again, R star is just going to be the marginal product of capital minus 1. So that's going to be this guy right here. I know from before that savings is beta over 1 plus beta times the marginal product of labor, which is going to be this guy right here. K star is 1 over the population growth plus depreciation rate. And so if I plug in the numbers for population growth being 0 and delta being equal to 1, that's just a 1. Then I have beta over 1 plus beta, 3 K star to the 1/4. So I'm just going to solve it for K star. So I'm going to get that K star, once I do all that math, becomes 2 times 2 to the 1/3. So that's also equal to savings. Because we have full depreciation, that means that capital is exactly equal to savings. Again, I can go back and I can use that to figure out what W star and R star are. Now the big thing here is when I solve for R star, So that's a negative 1/2. I can use all of those things to get CT old and CT young. And really the main thing that I want to talk about here is when I get all of these results, I know that I have perfect consumption smoothing here. I know what my savings is, but the real issue here is that I got a negative interest rate. And we saw before that if beta was greater than 1 plus r, then we're going to oversave. But here we have 2 compared to 1/2, so beta is definitely bigger than 1 plus r, which means we're going to oversave in this economy, and the fact that we're oversaving is what we call dynamic inefficiency. And what that basically means is there's some sort of Pareto improvement to this allocation between the young and the old generations that exist. And so we want to think about, well, how can I find that Pareto improvement, given that now I know that there's some sort of dynamic inefficiency in the model. So what we're going to do in the next couple parts of these videos is we're going to think about how we can find that Pareto optimal allocation, how we can use some policies like Social Security and taxes in order to get to that Pareto optimal allocation. And as we go through, there's going to be a lot of math and a lot of model assumptions. But I think once we get through all that, again, if you can keep in mind that the big idea is we want to prevent this oversaving, we want to get a Pareto improvement out of this model, I think it'll help make a lot more sense. So again, if there are any questions or points you want to clarify, feel free to put that in the comment section below. But if this video or these videos in general helping you out, please like and subscribe. We'll see you next time for another case of econ struggles.